Recording in
Hello and welcome
progress.
back to our continued conversation of colligative properties. We just came from discussing the colligative property of vapor pressure and specifically the phenomenon called vapor pressure lowering. And now we're going to look at the cousin of the colligative property that is vapor pressure lowering, which we call boiling point elevation. And the reason I call the boiling point elevation colligative property something that's like intrinsically related to our vapor pressure lowering is because there's a direct connection between the boiling point of a substance and its vapor pressure. So let's get going. So I've started here by asking us, how does the addition of solute affect the solution's boiling point? Before we can answer this question, I think it's a good idea for us to remind ourselves of what a boiling point is beyond just the temperature at which a substance boils. So define the boiling point of a substance, T comma B, or no, sorry, T sub B. There we go. So yes, this is the temperature at which all molecules in a substance convert from the liquid phase to the gaseous phase. But more important, well, not more importantly, but I think more relevant here to our conversation about colligative properties is we have to remember that if all of our molecules have gone from the liquid phase to the gaseous phase, that means that the atmospheric pressure that was once bearing down on the vapor above our liquid has to be equal to the total pressure of our overall particles that are now fully in the gas. We've established a pressure equilibrium. So we can kind of frame this idea of boiling point as being the temperature at which the vapor pressure of a substance, the pure substance, is equal to atmospheric pressure. So I've got this little diagram here, which is showing vapor pressure lowering, right? So same idea as we discussed in our prior videos. Here we have these red plus signs indicating our solute. Which means that our little blue circles, those are our solvent particles. And we know from vapor pressure lowering that the presence of these solute particles is physically preventing those solvent particles from escaping into the vapor phase. So if fewer molecules specifically solvent, assuming we're an ideal solution with a non-volatile solute, vaporize due to solute presence, then in order to get every single one of our solute particles out of the liquid phase and into the vapor phase, so all of these blue in the bulk liquid become blue vapor particles, right? That's what it means for us to boil. Then we need to increase the amount of energy available for the solvent particles to use as kinetic energy to navigate around the solute. So if these solvent particles were moving a little bit more quickly, right? We're providing more energy, typically thermal energy, then we can find them statistically more able to make it around that solute particle that's blocking its path and escape into the vapor phase. So this means that the point at which all of our particles in the solution, all of our solvent particles that are in solution, by the time that all of those solvent particles that are in solution have made it up into the vapor phase, that's the point at which we've boiled. So we've got to add more energy, more thermal energy, in order for us to get every single one of those molecules into the vapor phase. So if we need to increase the amount of energy available, this means that we have to increase our temperature until we reach a higher boiling point than compared to what we would expect to see in the pure solvent, right? So this is how we might expect the boiling point to be affected by the addition of solute. So our solutions are going to have different boiling points because we need to give those solvent particles more thermal energy for them to convert into kinetic energy so they can navigate around the solute and finally have every single last one of them escape into the vapor phase, which is the point we call boiling, right? So it's the exact same idea. There's a reason why I said this is related to vapor pressure lowering. So if we are lowering the vapor pressure, then in order to raise the vapor pressure, we are going to have to heat our solution up. And in order to raise the vapor pressure so that it is equal to atmospheric pressure, so we're trying to take this vapor pressure and increase until it is equal to atmospheric pressure, that is going to require a higher input of energy. So same idea. How do we quantify this? So in looking at vapor pressure lowering, we looked at Raoult's law. So we saw a direct proportionality between how much vapor pressure our solution has compared to the mole fraction of solute that is remaining in solution. Because the change in vapor pressure is proportional for change in solute concentration and the solvent concentration, it makes sense then that the boiling point change is also going to be one that is a proportional one. Because again, boiling point and vapor pressure are related. Boiling point is the temperature at which our vapor pressure is equal to atmospheric. So let's define boiling point's elevation. This states that the addition of solute to pure solvents, and again, we are mostly assuming here that we're dealing with our ideal solutions and non-volatile solutes. So the addition of solute to our pure solvent affects a proportional increase in the boiling point of the solution compared to the boiling point of the pure solvent. In other words, as we increase the concentration of solute, then the change in our boiling point, meaning how much it has risen, so the rise in boiling point, is going to get larger because we're going to have more and more solute particles that we have to provide energy to our solvent particles to navigate around. So it's like we have more things in the way. So we need to give the solvent particles more energy by increasing the temperature so they can navigate around those things. So again, if we've got one thing that trends in the same way as a result of something else, so like one thing increases and another increases as a result, or one thing decreases and so too does another, we call these direct proportionalities. And we express this directly proportional change in our boiling point using what's called the boiling point elevation equation. So we say here that the change in the boiling point of our solution is equal to K times I times M. So this is our boiling point elevation equation, where our change in boiling point, delta TB, is equal to the boiling point of our solution compared to the boiling point of our pure solvent. So that is how much higher our solution's boiling point is compared to the pure solvent. K is called the boiling constant. This is something that is specific or unique to the solvent. So KB, just to indicate it's the boiling constant for water, is equal to 0.519. I believe that's correct. There's so many constants in chemistry, guys. So boiling constant of water, 0.512, not 519. So 0.512 degrees C per mole. Okay, I'm gonna just shrink this guy up. We can look at it in a moment. I is our Van't Hoff factor, which, as discussed in lab, tells us the actual number of particles that one molecule of solute contributes to solution. So for instance, our electrolytes, aka our fully soluble ionic compounds, those things that dissociate or split into ions, those are going to have a Van't Hoff factor that's greater than 1, because again, colligative properties are ones that depend on how many things are present in solution that are blocking the path of your solvent molecules. So if I've got sodium chloride that I'm dissolving, for example, I don't just have molecules of Na and Cl, rather I've got two ions, Na and Cl. So I have to indicate that this effect has a doubling that's included because I've now doubled the amount of particles that are actually present to block the solvent. Okay, and then this means that lowercase m, this is the molality of the solution. And remember, molality is moles per kilogram solvent. So don't conflate solute and solvent. Or excuse me, solution and solvent. Language, right? Don't do what I'm doing. So moles per kilogram solvent. Let's get some kind of color coding here just to, I don't know, make this less difficult to get all these parts visually. So here we have the definition of our change in boiling point. Here we have our freezing constant, excuse me, our boiling constant. We're talking about boiling point elevation, not freezing point depression, not yet. And then we also have the Van Hoff factor. If you are looking at a polar covalent solute in water, Van Hoff factor is 1, right? There's no dissociation. So maybe just to highlight here. Oh, I have that backward. That's not blue. There we go. Blue is here. So Van Hoff factor, number of particles that one molecule of solute contributes to solution. So like sucrose, for example, which we've talked about a lot in this conversation. Oh my God, my dog. Would have a Van Hoff factor of 1. And then we have the molality of a solution, which is again a concentration unit. Okay, so since my dog's freaking out and the doorbell just rang, I will see you in our next video.